This is a tutorial for graphing rational functions. I'm going to give you a step-by-step tutorial over just one example. And rational functions are like people. They're all a little bit different, but if you follow the rules that I use for this one, they should help you with most of the rational functions you come up with. Top-heavy rational functions, even though they follow the same rules, look a little different. If I get a chance, I'll make a tutorial that involves a top-heavy rational function later on. Well, let's go ahead and get started. I want to graph the rational function y equals x squared minus x minus 12 over x squared plus 5x plus 6. The first thing I want to do is factor this out so I can have my function in factored form. Well, to factor x squared minus x minus 12, I need two numbers that multiply to give me negative 12 and add to give me negative 1. Those numbers, my magic numbers, would be negative 4 and 3, so I can factor the numerator as x minus 4 times x plus 3. For the denominator, I need two numbers that multiply together to give me 6 and add together to give me 5. Those numbers are 3 and 2. So I can write the denominator as x plus 3 times x plus 2. f of x, y equals, there's my function in factored form. Now that I'm in factored form, I can begin my next step. Okay, so you see my rational function in factored form, and the first thing I want to do, and it doesn't really matter what order you do these in, but I always find the points of discontinuity first. Points of discontinuity are where I actually would have to pick up my graph, my pencil on a graph, in order to continue graphing. And in a rational function, these are only going to occur where your your denominator is equal to 0. If your numerator is equal to 0, that's not going to cause a point of discontinuity unless it also calls to 0 in the denominator. So in this particular case, for the denominator to be equal to 0, I would have x plus 3 times x plus 2 is equal to 0. If a product is equal to 0, one of the factors has to be equal to 0. So either x plus 3 equals 0 or x plus 2 equals 0, which tells me that x equals negative 3 or x equals negative 2. My 2 points of discontinuity are at x equals negative 3 and at x equals negative 2. Points of discontinuity are either going to be a vertical asymptote or they're going to be a hole. Remember that my two points of discontinuity in this particular graph are negative 3 and negative 2. How would I know whether it was an asymptote or a hole? Well, I look at the factor that gave me the 0. For negative 3, the factor that gave me the 0 is this x plus 3. Then I look to see, is that same factor found in the numerator? If the factor is found in the numerator in the same or higher degree, then it must be a hole. So I have a hole at negative 3. Let's look at the vertical, or negative 2. Negative 2 appears in the denominator as the factor x plus 2. That's what gave me the 0. Is x plus 2 in the numerator? No, it is not. If it shows up in the denominator but not in the numerator, or in the numerator with a lower degree, then what I have is a vertical asymptote. I have a vertical asymptote at x equals negative 2, sometimes called a VA for whatever reason that might be. Now, if it's a vertical asymptote, which I had at negative 2, vertical asymptote is a vertical line, I can write that as x equals negative 2. I'm going to have a vertical asymptote at x equals negative 2. If I have a hole, however, a hole is a coordinate point, and I need to be able to find the y value of my coordinate point. I know the x value is going to be negative 3. Okay. Now, how am I going to figure out what the y value is? Well, what I do is, negative 3. What I do with this negative 3 is, first of all, I cross out the two factors that gave me the negative 3. And then I plug in negative 3, because that is the point of discontinuity, into what's remaining in the function. Okay. So my y value is going to be equal to, in this case, negative 3 minus 4 over negative 3 plus 2. There's my negative 3 minus 4. There's my negative 3 plus 2. Well, that's going to be equal to negative 7 over negative 1, which is 7. So my hole is negative 3, 7. My vertical asymptote is x equals negative 2. You could have numerous holes or no holes. You could have numerous asymptotes, vertical asymptotes, or no vertical asymptotes. You just have to figure out how many you have by looking at the points of discontinuity and then just determining is that same factor found in the top to find out is it a hole or is it an asymptote. The next thing I want to do is I want to figure out does this graph have a horizontal asymptote? Well, for all the functions we're going to do, you're going to have at most one horizontal asymptote. And the way we determine whether or not a function has a horizontal asymptote is by determining is the graph top-heavy, bottom-heavy, or neither. If the graph is top-heavy, that means the degree of the numerator is greater than the degree of the denominator. If it's bottom-heavy, the degree of the denominator is greater than the degree of the numerator. And if it's neither, apparently the numerator and denominator both have the same degree. You can pause and take these notes if you want. I'm going to move on so the video doesn't last for an hour or so. Okay, what I want to do with these, now that I know if the graph is top-heavy, bottom-heavy, or neither, I can use that to determine what my horizontal asymptote looks like if it even occurs at all. If I have a top-heavy equation, I am not going to have a horizontal asymptote at all. It will have what's called a slant or oblique asymptote, but I'm not going to do that in this tutorial. Possibly in a later tutorial I'll show you how to find the slant or oblique asymptote. If a rational function is bottom-heavy, where the degree of the denominator is greater than the degree of the numerator, then my horizontal asymptote is always y equals 0. If a rational function is neither top-heavy nor bottom-heavy, the degree of the numerator and the denominator are the same, I take the coefficient of the leading term of the numerator and divide that by the coefficient of the leading term of the denominator. Then y equals whatever that number is will be my horizontal asymptote. Okay, if you already know what to do with your horizontal asymptotes, I'm just going to give a few examples to try and explain what I did on the previous slide. You can go ahead and forward the video till you get to the next slide because that's all this is for. Give a couple examples. Okay. Suppose I have y is equal to x to the fourth minus 3x cubed plus 2x plus 1 over 5x cubed minus 2. Is this graph top-heavy, bottom-heavy, or neither? Well, the degree of the numerator is 4. The degree of the denominator is 3. This graph is top-heavy. It will have no horizontal asymptote. What about y equals x to the 6th minus 3x plus 1 over x to the 8th minus 4x to the 5th plus 2x? Doesn't really matter. The only thing that does matter is the degree of the numerator and the denominator. The numerator has degree 6. The denominator has degree 8. So my function must be bottom-heavy. If it's bottom-heavy, my horizontal asymptote is going to be y is equal to 0. Okay. And finally, let's look at 5x cubed minus 3x squared plus 2x minus 4 over 2x cubed minus 2x plus 5. My handwriting leaves much to be desired. I try to get my classes foreign language credit if they can understand my handwriting, but so far it hasn't paid off. Anyway, the degree of the numerator is 3. The degree of the denominator is 3. Okay. This is neither top-heavy nor bottom-heavy. How do I figure out the horizontal asymptote? Well, the horizontal asymptote, if you're neither top-heavy nor bottom-heavy, is y is equal to the coefficient of the highest degree on the top divided by the coefficient of the highest degree in the bottom. And so my horizontal asymptote in this particular example is y is equal to 5/2. In the problem I'm working on, y is equal to x plus 3 times x minus 4 over x plus 3 times x plus 2. Remember, I factored this out before it was factored. My equation was actually x squared minus x minus 12 over x squared plus 5x plus 6. This graph is neither top-heavy nor bottom-heavy because the degree of the numerator and denominator is both 2. What's the leading coefficient of the numerator? It's 1. The leading coefficient of the denominator is 1, so my horizontal asymptote is going to be y is equal to 1 over 1, which is y is equal to 1. Okay, now I want to find the x-intercept. The way you find the x-intercept is, well, you always find the x-intercept by setting y equal to 0. I've given you what I call time-saving notes. You don't have to use these, but they sure work a lot better. And you can copy down the notes, but I'm going to just show you what I do. First of all, if I see the same factor in the top and the bottom, I scratch it out. Second of all, if any factor I have in the denominator, I scratch out. I give a proof of that some other time. I kind of gave a little idea of the rules down here in this mess. Okay. But once I'm through, I just set whatever else is equal to 0. So 0 is equal to x minus 4, tells me x is equal to 4. So when y is 0, x is 4, that tells me I have an x-intercept at 4, 0. It's just that easy. If I had another one up here, x minus 3, then I would have actually two zeros. I would have a 0 at 4, 0 and a 0 at 3, 0. But in this particular case, I have one x-intercept. That x-intercept is 4, 0. How do I find the y-intercept? Well, I find the y-intercept by setting x equal to 0. Just like before, though, these two numbers I can cancel out, and there's a very easy to see reason for that. But I just go ahead and cancel those out, and then I plug in 0 for x. So I've got a 0 here and a 0 here. It tells me that y is equal to negative 4 over positive 2. Y is equal to negative 2. So when x is 0, y is negative 2. I have a y-intercept at 0, negative 2. That's how we find our y-intercepts. All right, let's put all this stuff together. Going back through your notes, you can see the first thing that I noticed was I looked for my points of discontinuity. I had a vertical intercept at x equals negative 2. I had a hole at negative 3, 7. Negative 3, 7. So I've got this hole up here at negative 3, 7. Then I found I had a horizontal asymptote at y equals 1. Notice I'm labeling everything even though I haven't really drawn my scale. Then I looked for my x-intercept. I found out that I had an x-intercept at 4, 0. My y-intercept, I had a y-intercept at 0, negative 2. Okay. And in the cases that we have, we're not going to worry about crossing the horizontal asymptote. Please, please, please do not believe that you can't cross a horizontal asymptote, because there are many graphs that do. But in this particular case, we are not going to be crossing it. That would once again make my tutorial too long. So let's see what I've got. Here I am. I'm going from this point to this point, and then I'm going to come up to the y equals 1 asymptote, get closer and closer and closer to it. Coming this way, it looks like I'm heading down. I'm going to continue to follow by my vertical asymptote, x is equal to negative 2. This x equals negative 2 actually came from this factor x plus 2. Its degree is 1. If that factor has odd degree, the end behaviors about the asymptote are going to be different. If it's odd degree and it's going down on this side, it must be going up on this side. Well, it has a hole at negative 3, 7, so I have to actually get to the hole. I'm going to make sure I can still see the hole and write the coordinates of the hole. Then it's going to continue down until it gets to this asymptote. Okay. Once again, I will show you in a later video how to determine whether or not we actually do cross this horizontal asymptote. But for now, we're just going to leave our graph looking like this. In fact, to me, that's everything you need. Okay, I see all my vertical asymptotes, I see my horizontal asymptote, I see my intercepts, and I see a sketch of the graph. Okay. Now, what is the domain of this graph? Well, the domain is all the points x except for those that were my points of discontinuity, which is x can't be negative 3, x can't be negative 2. If they ask you to write this in interval notation, you would say the domain goes from negative infinity to negative 3, picks up at negative 3 and goes to negative 2. I didn't save myself enough room. Picks up at negative 2 and goes to infinity. What about the range? Where am I not seeing a y value? Well, I've got y values all the way up here until I get to this horizontal asymptote. My y cannot be equal to negative 1. I'll never get a y value of negative 1 unless I had crossed the asymptote, which I just promised you and you took on faith didn't happen. But there's one other spot where I don't get a y value. Right here at the hole, negative 3, 7. That's 7. Look, I can get up to 7. I can be over 7, but the 7 itself isn't there. So y also cannot be equal to 7. Those are the 2 points that are not in my range. If they ask you to write it in interval notation, you will go negative infinity to negative 1, pick back up at negative 1 and go to 7, pick back up at 7 and go to infinity. I hope this helps. Study hard, and we'll see you in class.